All right, welcome back, my friends. First off, this is William M. Briggs. This is going to be episode 45, The False Hope of Falsification, or Falsificationism. I apologize for missing a week in the class. We had a massive ice storm come through northern Michigan last week on the 29th. Lost power for a long time, a week. And there was absolutely no chance of doing any recording or anything like that. So I'm back in business now and slowly catching up. I've got a whole week's worth of work piled up from the stuff that I missed. I had no internet, no email, no nothing. And no class. But now we're going to jump right back into it. We're still on causality. And part of causality has to do with falsification. So the idea of, we're going to talk about all this, but falsificationism is an oft-beloved criterion in science. And while it has some merit, we're going to see today it has very little merit, and it's not that interesting. As it turns out. So let's look at that and try to explain where, I'm not saying that it has no uses, but I'm saying it practically has very little use and is not often found to be of any value in most in scientific practice and so forth. So you might have heard a guy named George Box, and there's a shortened quip of his that runs something like this, that all models are false. His exact quote is, I have it in, if I booger this up, I have it in the book. He said, all models are wrong, he said. The practical question is, how wrong do they have to be to not be useful? Well, that's got a lot of negatives and it's hard to mouth, but it comes out to be this. All models are false, but unfortunately, that is false. It's not true. Some models are in fact true, and they're good models, and there's all kinds of them. So the most interesting one, of course, one of the most common ones, I don't say it's the most interesting one, is so for instance we have a bunch of let's just use this for our generic schema like this. This is going to be where y is going to be a head on a coin flip. And then y is going to be a head on a coin flip, probability of a half. And x is going to be our usual thing. We have a two-sided object, which when tossed, this is the premise now we're saying. These are our premises. We can only get h or t, and must take one of those things when flipped. If we take those premises, which are useful for regular coins in operation, it's a half. Everybody knows this. We've talked about that ad nauseum. It is a good model. This is a true statement because these are true facts about actual objects in life. And therefore, this is a good model. It's not a false model. It's also a useful model. It says nothing to do about cause. Models don't have to say anything about cause. Models can be probabilistic. That's what this whole class is about. I mean, we're always after cause. Once we've identified cause in its full flower, the full explanation of why something is, why and how something came to be. You know, it's material cause, it's efficient cause, it's formal cause, and then finally it's final cause, or the reason for its being. Once we have identified something in that full flower, I guess, of causation, well, then we're done. And that's what we're always after, trying to find the true nature of nature, the true essence of nature. But we can't always do that. And in fact, we know that we cannot, and certain parts of nature are forever closed off to us. This is what quantum mechanics has taught us. Okay. So this is a true model, and it's useful, and it can't be falsified, as we're going to see. So Box is wrong. A lot of models are bad models. So, but falsification has some purpose. So, for instance, suppose we have x plus 2 equals 7. This is a premise in our model, and you know. We're working with logic here. Probability is logic, so we can have this. And someone insists, say a student in class, that x equals 2. accepting this, given this, they say the probability that x equals 2, we could write it out in probability. There's lots of different ways. Remember, it's just notation. There's lots of different ways to write probability notation or logic notation. The probability x equals 2 given x plus 2 equals 7, and all the tacit premises that we come along. After all, there's a tacit premise saying what that is. There's a premise saying what that is. There's a premise saying what that is. There's a premise saying what that is and what this means. That's the model, but if someone came out and said, given this and some hidden tacit premise they didn't write down, the probability is 1, well, that model has been falsified. It is said the probability that x equals 2 is the case, and it's not the case. So that model has, in fact, been falsified. And that's no problem. Okay, so falsification is right. So we use falsification to rule out errors like this. There's absolutely no problem with this. Okay, so let's try to think about this more generally and see how far we can push falsificationism and then see where it fails. All right, so let's just change our notation slightly here. The probability of y, whatever y is, it's just some proposition of interest that we're going to write down. It could be very long, it can be very short. It could be complex and compound. It could be brief and singular, whatever. And here m is model. We're gonna investigate model, but model again can be a simple premise. It could be a string of premises. It could be premises and observations, all kinds of math. It could be acres long, but it's still going to be some model. So if the model said the probability of y, whatever this y happens to be, given the model, is 1, and we observe the contrary of y, whatever that's going to be, the logical contrary of y. If it says our model insists tomorrow it will absolutely rain with 100% probability of rain tomorrow, and in fact no rain whatsoever, 0 rain, not even a hint of rain, completely sunny day from start to finish, and then a full moon at night, nothing. This model M has been falsified. M has been falsified. No problem with that. We can understand that kind of a statement. There's no difficulty. There's no logical difficulty. But what if we had said like this? So what if instead we had a statement like this? We had, which is the way most models are interpreted, as I'm going to try to argue to, 1 minus epsilon, where epsilon is some number greater than 0, no matter how small, even infinitesimally small. In other words, the model said that y is going to happen with probability 1 minus epsilon, where this is something less than certainty. And again, we observe this model has not been falsified. It has not been falsified. False and true are as strict as criteria as you could get. There's none higher. It's either true, definite, or false, definite, end of story. A lot of people will try to say, well, if we observe this model has been practically falsified. The model has been practically falsified. Practically falsified, the term, you'll hear it all the time, practically falsified has exactly the same logical status as practically a virgin. The same exact logical status of those. In other words, both are suspect. Both are suspect. Both don't mean what they say. It's either falsified to core or it's not falsified. There's no in between. All right? When people say practically falsified, they mean the decisions that they would make using this model are okay with them. There's fuzz around this. And in fact, that's exactly what happens in all these scientific models that are in use. Fuzz is invoked all of the time. When a beloved model goes wrong, and it happens all the time, they say, well, I didn't really mean the probability was going to be exactly 1. I meant it would be mostly 1. And really what I meant to say is, let's see here. What I really meant to say was I meant to say it would be the probability of y plus or minus fuzz equals 1. And if you allow me some fuzz, why then I can claim my model was good after all, or something like this. That's what happens all the time in real life. When you have some, you'll see people claiming, guys on our side, they'll say, you know, these global warming models have been falsified because they'll predict, for instance, an average temperature. We'll just make a number up here. It doesn't make any difference. And we'll use civilized units. The temperature, the probability, like the global average temperature will be, Y will be 70 degrees Fahrenheit, according to the model. And that's what the model spits out. The model spits out this number. It says it's going to be 70. So any kind of model just spits out a single number or something like this. And of course we observe, say we observe Y equals 70.001 Fahrenheit. This model has been falsified. The model says 70 would happen. It wasn't 70. It was not 70. This is not 70. You might say, oh, it's close enough. It'd be close enough for a decision you'd make on it, but that doesn't mean that Y is 70. That's an entirely different thing. We'll come to how to decide about models in the future here. But this model has not been falsified. And in fact, that's exactly what happens. People will say this 70, what I really meant is I didn't really mean 70. I meant 70 minus plus or minus fuzz. And all of a sudden, the model has been rescued. Or they'll say this wasn't a fair test, and and so what they'll do is they'll say, well, I really didn't mean everything I said in M. Okay, so now let's look at M, because Karl Popper. It's very difficult to catch anybody on a falsified model. Karl Popper was right in a sense. This whole idea of falsification. He said a model must be falsifiable to be scientific. And a lot of people praise this statement and agree with it. It's wrong. It's absolutely wrong, and I'm going to prove to you it's absolutely wrong, and you're going to agree with me. It's actually easy to see that it's wrong. But the spirit of it was good. I agree with that. The spirit of, there's a lot of people that cling to very lousy models, like say the astrological columns you read in the newspaper or something like this, where people read their astrology, or was it the horoscope of the day or something like this, and they read into it all kind of, we'll see what I mean by reading into the model, all kind of things that aren't written there. And they're going to say, yeah, it's a good model. It's not perfect. It's not perfect, but it's very accurate for me. And so this is frustrating when you want to show these people that what they're thinking is just wrong, but you can't get to them because they're so enamored with the model itself, they can't give it up. And that was Popper's kind of thinking. Let's try to find a logical test that we can exclude these kind of models before even having to look at them. So if the model's not falsifiable, we don't need to look at it. Well, it just doesn't work that way, because no, scientists don't treat their models, and they treat the same. All scientists who love their creations treat their models in exactly the same way the horoscope lover treats her astrological. Did I make the right word? Astrological models. They act in exactly the same way, psychologically speaking, although one may use more math than another. So let me prove to you. But let me just talk about, make sure I want to talk about this. Yes. Okay. So let me just describe something here. So any model is a list of premises. Premises 1 and 2 and 3, and let's say there's m of these, where any one of these, for instance, may be premises m might be our observations, maybe observation 1 and 2, and there'll be n observations, something like this. And any one of these might be, so for instance, like P, J may be, some other proposition, W1, anded to, or ORed, let's OR them, with W2, and this must be ANDed with W3 or W4, and so on. And there's a whole host of tacit premises. These models are just an enormous length of premises and computer code and observations that go into them and so forth. So if a model is falsified, if a model said probability y equals, the probability y m equals 1, and we observe y this means the model has been falsified. The model is false. That means something in this entire string of premises is false. We don't know what. You can't tell logically just from this. If the model did say the probability of this is certain, and the model is this list of statements, this huge list of statements, it says that one of these premises, or more than one of these premises, is itself wrong. Which one? Doesn't say. We have to figure out outside the model. All right. So that's one way to think about this. So when models go wrong, we have to, obviously, we look into the guts of the model to try to discover what's going on. But here's the kicker, so that this is one model right here. We'll call this model N right here. This one right here is model N, which has this particular premise at the very end, which has the observations of the world that we might use to inform this model. Model N plus 1 is exactly the same as M, but with the idea that it's exactly this, but with the idea that PM like this, PM prime, for instance, where PM prime is exactly PM union with ON plus 1. So this obscure, ridiculous notation, which I'm probably confusing more people than I'm helping. The idea is if I add one more observation, I've just talked about this before, I have a new model. I have an absolutely new model. That's not the way it's treated in science and so forth. Say that P3 is the math of it. We discussed this before. If this is where all the math and the theory reside in this set of premises here, which may be this long, complicated form here, they consider this the model. But it's not the case. You change any premise in your argument, in a logical argument, you've changed the argument. It's in a new argument. It's an entirely new argument. We have to stay strict on these logical lines, or we're forever gonna be lost. Okay, so that's going to be the case. All right, so now let's try to always keep this in mind, because we're going to start looking at models very soon, and we need to make sure that we always have the idea that we change something, anything on this side, and it becomes, and if the probability of y changes, then the model itself is different, okay? That's just the way it is. If we add a premise to this thing, like a truth, the probability of y won't change. And so this model, adding a truth, is equivalent to the model without the truth. So we have to think of this stuff in logical terms. So because Popper was trying to give us a logical criterion, and failed. So let's look at this. Okay, so let's suppose we have the probability that y equals some small y for different circumstances and so forth for all y. And I'm sorry. So that this is going to be some probability for all little y. This model right here, the probability that, so whatever it is, so we're talking about temperature forecasts for tomorrow that come out of something called MOS, Model Output Statistics. We're talking about linear regression, or all the models used in sociology or psychology. And indeed, quite a lot of models in physics and statistical physics, and the evidence that they used for the Higgs boson and so forth, and all these kind of things. They're models like this. They'll say the probability of some observation y, whatever the y's are going to be, for all y, is going to be some number between 0 and 1. This model is not falsifiable. Can you see that? Because if the model said the probability of y equals epsilon, And in fact, we observe y equals y. If anything, this model has been confirmed. The model said there was a probability, epsilon, of course, I should have said so. That's a tacit premise of mine that people know what epsilon. Epsilon always means, or almost always means, a number very small, close to zero, very close, as close to zero as you like, but never reaching zero. And I'm sorry that I assumed that everybody would know that. Maybe everybody doesn't know that, but that's just it's just a lingo, okay? It's just a convenient way of writing. I'm giving this thing a very small probability, but it happened. The model's not been falsified. If anything, again, the model has been shown to be correct. It says that there was a possibility for this to happen. This, in fact, happened. The model was right. Okay, the model was right. Oh, and look what I did here. I violated one of my classic rules. You guys should, I don't hear anybody yelling at me. I didn't make the probability conditional. I used shorthanded notation, which can be helpful, but often hinders. Okay, so this model is not falsifiable, and that includes the great class of models that are in use. And almost all science models is like this, okay? Almost all scientific models are exactly like this. They say that anything that can happen, especially if we're talking about a regression, for instance. In a regression model, if I can do this, here's the probability density for a normal distribution. We didn't talk about normal distributions, but basically the areas that are higher on the curve are more probable than the areas that are lower on the curve. This is the probability density on this curve, the density. I'll describe what I mean by all that, but you can just take it as the probability for right now. This remains above infinity, and this remains above zero, I should say. Here's zero over here. This line remains above zero, and this line remains above zero until you get to infinity. So whenever you're using a normal distribution, which you are all the time, anytime you use a regression and so forth, your model is of this form. In fact, almost any statistical model is going to be of this form. Not all of them, but almost anyone that you're going to see being used, and practically any research shows paper or something like this. These models are not falsifiable, simply because therefore they're not scientific, according to Popper. But that's simply the greatest class of models in use. And it's the same, I told you, it's the same in physics, it's the same everywhere. Unless the model says, again, I've said this 100 times already, unless the model says that cannot happen, with absolute certainty, cannot happen, and then it does, that model has indeed been falsified. That's the only time falsification works. And here, it's even worse than you think. It's even worse than you think. Let me give you another example right here. So this, I hope you see this. If you don't see this, please let me know, because this is it. This is almost all models. And we haven't really talked about models yet, so I haven't really proved to you that this is the way most models are, except by just saying it. So, but I will prove it to you. All right, here's another thing. So for instance, let me give you this example right here. So the probability for x, or it doesn't matter, x or y, I'm just x given m equals p, which is greater than 0. Can even be large. But we know by evidence outside of m, that that x is impossible. Well, let me give you an example. Let me give you an example first. I shouldn't have done that. I'm still catching up on my notes. You have to forgive me for this lecture. I'm a little bit discombobulated. I had an enormous cedar tree fall on the shack here where I'm making these recordings, and I had to chainsaw all that away. There's a little bit of damage on that, but I got it cleared away just in time for this. But let me give you another example here. So I'm going to use an example later about grade point average. Using regression, because I got it out of some paper somewhere. I can't remember where, but I'll look it up. But by the time we use this kind of a thing. But this happens all the time. Absolutely all the time. Anyway, the probability of grade point being less than 0, according to the model, is greater than 0 because they use a normal distribution. They use the regression. This model is not falsifiable, even though we know that you can't have a grade point less than 0. You cannot have a grade point average less than 0. Maybe there's some obscure place out there that computes the grade point in such a way that you can, but I'm taking it as you can't. So this model itself, even though it's absurd, is not falsifiable because we have evidence outside this model. That's what I was trying to say. We have evidence outside M that says the observable is impossible. The observable values, certain observable values are impossible. So this is giving probability to values that we know outside the model can't be seen, are impossible. However, it's also giving values, probability values that are not certain to values we know are possible. So this model is again not falsifiable, but this kind of stuff is used all the time too. In fact, it shouldn't be. This one's fixable. The first one, where the probability of any observable we see is not exactly 1, for any observable that we see is something like 1 minus epsilon at the worst case scenario. Those models are just not falsifiable, right? So we probability of y equals little y given m is at least 1 minus epsilon for some y, Those models aren't falsifiable because it didn't say anything was impossible. Here we know that we have impossible values from knowledge outside the model, but the model itself is not falsifiable. This one's not fixable unless we knew all the causes that were involved. This one is fixable, but this stuff happens so much because of something called parameter-centric analysis. And we're going to talk all about parameters, what they mean, and why they shouldn't be used. I mean, they should be used. I scratch that saying. They absolutely should be used. But they shouldn't be the focus of the analysis. The focus of the analysis should always be on observables. All right? That's what science is about, observables. But because of this weird cult of significance and all this kind of stuff, the focus has become on the internal guts of models, on these parameters and so forth, which they mistake for observables all the time. That's a big fallacy. We'll talk about all that. All right. So, whereas falsifiability has some uses, it really doesn't in practice, because although it's a wonderful thing, nobody ever accepts it. When you show a scientist a model that you claim his model is wrong, chances are he'll say something went wrong in the experiment. This one doesn't count for this and that reason. He used all the same excuses that the woman defending her horoscope will use to retain that model. So falsifiability isn't that interesting. Although we should always hold people to their predictions and so forth, but it doesn't mean you're going to convince them. There's no perfection in life, and we're not going to see any. I mean, we can come up with all these formulas and the correct way of doing anything. It doesn't mean it's going to work on anybody. All right, there's just absolutely no way people are going to be converted to all this stuff, because that's just human nature, and scientists are just as human, even though it doesn't seem like it, as anybody else. Like I say all the time, scientists are excellent at finding evidence which comports with their views or supports their views, but they're even lousier than ordinary people at finding evidence which disconfirms their views. That's the curse of intelligence, if you like. Okay, that's it for now. There's more down below, wmbriggs.com, wmbriggs.substack.com. The links will be in the description, all that kind of stuff. Sorry for the hastened use and the kind of chaos of this. Next week we should be back on track. Most of the stuff should be cleaned up here, and I'll be ready to go. Thanks very much for listening.